Okay, Math 2400, Lecture 8, Random Variables, Hypergeometric and Negative Binomial Distributions. So, let's see. Hypergeometric is this. Suppose we have m objects that are stored in a warehouse, and we know that s number of them are functional, s for success maybe, and f, which is m minus s number of them are damaged. We choose a sample size of n. What is the probability that x of them are functional? Okay, so this warehouse has m objects, and out of this, in some of them good, and some are damaged. Okay, so red, damaged, and green, functional. I'm not sure if you can see that. Yeah. So, and we choose a sample of size n. So I choose a sample of n. So my sample is n. And I ask this question: what is the probability that x number of them are functional? And you can see in this n, for example, 1, 2, 3, 4, 5, 6, 7, 8 are functional. Okay. So this can have a lot to do with decision making when somebody is buying some goods from a company and has to decide. So if there are more damage in that warehouse and the company knows that there are more damaged ones in the warehouse, then the price might be lower than the ones that come from a much nicer company with not damaged ones. So the person who is deciding should balance between paying too much and getting good things, and paying much less and getting bad objects. But anyway, that's something else. So, but this happens a lot. So this hypergeometric happens a lot, especially when you are dealing with a problem like this. So it can be in different contexts. Now, why I said warehouse, it makes more sense to tell the story in this context of a warehouse with some good objects and some bad objects stored. Okay, so let's see how we can. So we have to relate this to some random variable, and you can guess what we are trying to find is number of good ones. So let x be the number of functional ones in the sample of n objects. Random sample of n objects. Now let's see what we have here. First of all, we have fixed. These are fixed. M and n, and definitely, how many did I say? S. Did I say S number of them? I guess, yeah. S. So this is total objects in the warehouse and this is random sample, and this is damage zones. And fixed and find. So, or no, not fixed, let's say. Not fixed. Well, I should say that, whatever. So x, number of, no, s was the good one, sorry. Function, sorry, not damage, function. Number of functionals. Okay, so this is a like dependent. So this is what we have. Okay, let's see. So let's see what we can do. Let me erase this and go back to the way that I usually do this. So we have a random sample of n. Right? We have a random sample of n, and some of them are good and some are bad. So some are S and some are F, like success and failure. And we want to see in how many ways we can have, say, in how many ways we have like some successes here. And definitely there are some failures, right? There are some failures. So it's some kind of, say, okay, so we have so this has x, we are asking about x, so we have x, say functionals. X functionals among this n. We can ask this question, in how many ways we can choose x functionals in a sample of n. So we have, how many was that m? No, so that would be mx, and the rest are not functional. That is n minus m. Well, I guess that I will just, no, so, no, this is not m. I'm just looking at the problem. So that is, I had s, not m. So m was the total number, I guess, yeah, so s and m minus s, the rest of them will be damaged, okay? So, and how many are damaged here? It will be n minus x. Okay, so x of this are functional and n minus x of them are not functional. So in how many ways can I put them together? That is this way. So this is x out of s. There were s number, you see, damaged. Damage was m minus s, I guess, yeah. M minus s, and this was s. So I am choosing x out of S, and then definitely that will be n minus x out of m minus s. Now, in how many ways can I just choose n? In how many ways can I choose n? That is m. In fact, if you add this and this, you will get n, and add this one and this one, you will get n. Okay, so that is in fact like a combinatorial problem. We ask this question: in how many ways can we have n choices here, a random sample of n. Yeah, I got confused with the notation in the book. The book uses some n and something else, but I just used another notation. That's why I got confused. So I have chosen a sample of n objects, and it's like true. I'm just saying in how many ways I have x damaged ones in this sample of n, and that is like choosing x out of S. And okay, so that is the number of ways I can choose x out of S damaged ones. Sorry, functional ones. I should have now functional. X functional ones, and definitely this is a sample of n. So n minus x of them are damaged. And how many damage do I have in the whole warehouse? That is m minus s. So this should be multiplied by this, because the rest of them are this type, they are damaged ones. And it's like choosing x out of s and n minus x out of m minus s, right? This should be multiplied. It's like I'm choosing, say, two types of something, and so I have to remember the principal counting, the formula that you multiplied them. So this should be multiplied by this, and then in how many ways can I choose n objects out of m? No order. That is this. So dividing this by this, it will give me this probability. Now this x has to be, this x can't be more than say n, right? First of all, and also the n can't be more than the whole warehouse, and there are some restrictions. So x belongs to this. Let me, since the book is using some x belongs to my, let's write it like this because it has maximum something. Maximum of volume with 0 and n minus m plus s and minimum n I have to translate because I wrote m here, but the book has n here and m here, so that's why I got confused. But anyway, so that is hypergeometric. So it was basically accounting. Some people like to write, formulate this using probabilities, but I guess this is the easiest way to do that. And that is the formula for hypergeometric. I'm not sure if your calculator has hypergeometric, but it's kind of, the parameters of the hypergeometric is, the parameters are just too many. So you have m, you have this sample n, and you have this number x, and you have to be careful what x and n and all of them are. Like if this sample size can't be more than the warehouse, for example, and things like that. So this is a very you should be careful when you choose numbers, or well, definitely if it is a real life problem, that doesn't happen, because you just look at the number of objects in the warehouse and you don't choose more than those objects. So anyway, so that was the story of hypergeometric, And let me write the expected value and the variance of this hypergeometric. So expected value of this x. It's not that easy to find, so let me just copy from the book and oh gee, is n times what did I choose here? S over. And I have to translate. Oh gee, now let me just leave this to you. These are not really things that you will be interested, but it's in the textbook. You can look. Since I changed these things, I have to translate, and I might make mistakes. But that is in fact the expected number of good ones that you choose is this in n, a sample of n. And you can see the sample of n is here. And S over m is basically the probability that one that you choose is damaged, right? So if you pick one, is a number of good ones. Number of good ones and total number of good ones divided by total number is probability that when you choose one of them, it is a good one. Then you multiply by n. So it makes sense that this be the expected number of good ones. Okay, so let me erase this and discuss the other one. So negative binomial is like this. So suppose you are playing a game, right? So playing a game, like tossing a coin. And this game has two outcomes. So you do it one after another, and it has two outcomes. Two outcomes. Success and failure. So it has two outcomes, success and failure, and you played and you played. You're not restricted to how many times you play, but you do something like this. You say, okay, if I have n successes, I will stop. Or in this case, if I have say x successes, I will stop. Something like that. So you just play and play and play and play until you have x successes. So you just promise yourself that I will stop when I have like 5 successes, right? Now this can be just one success. You say I play and play and play and play until I just win once. Okay, so that's called a geometric random variable. So when that x in fact is 1. Okay, so how can we? So let's say the probability of success is P of success is like P, and then the other one will be 1 minus P, right? So this looks like binomial, that's why it is called binomial. So, okay, so now